Okay, we'll start. Okay, my name is Jin. I'm going to present the thesis work supervised by Dr. Nadia Figueroa on Gaussian persistent active exploration strategies in vision and touch. The content of the presentation will be first, we're going to discuss about like why we need active perception, and then we're going to talk about the representation for the shape of object or the environment. And we're going to go deep into how we're going to actually do the exploration. And I'm going to discuss about little implementation details. So first, the accurate understanding of object properties is important for robots to carry out the manipulated test. However, in most cases, a robot doesn't have a full information about the environment or the object. However, but three-year-old human or animals can actually explore the environment and learn about the environment. Therefore, we believe that active perception, defined as an intelligent data acquisition process, can empower the robot to actually learn about the environment and have a better capability carrying out the task. So this is a kind of a graphical demonstrate the formulation of the active perception. So where we have a kind of ground truth information about the shape or the object properties, then we have some kind of initial prediction of it. And then we are trying to find the camera pose or the contact points that will give us a maximum information gain about those kind of a prediction and try to explore it. So, I mean, Dr. Zenovici is here, but in 1987, Dr. Peter K. Allen and Dr. Zenovici provided kind of a demonstration of using a stereo vision system and the touch sensor during exploration. And in their future work session, I mean, there will be a current in future work session, they kind of bring up interesting direction to look into, which is first incorporating visual structure other than the geometry, and second, dealing with objects or the scene which has a complex surfaces, and then integrating multiple camera views and simulating the human tactile sensing in this kind of a in this thesis we try to kind of answer these kind of questions. So for related works for visual exploration, I will first explain about the differential rendering. So neural radiance field and Gaussian splitting now became a kind of a standard way to incorporate multiple camera views using a differential rendering. So they take the color images with the known camera poses or even a net images to estimate the shape and texture information about the scene or an object. Built on this, there has been many attempts in active perception to use this kind of a differential rendering to formulate the information gain, which can be used for the exploration. So in Penn, Dr. Costa Stanislav's lab proposed the visual RF, and Dr. Frederick Chowdhury's lab proposed active perception using a drone in this kind of a scheme. For tactile exploration, many people have used the Gaussian versus implicit surface, which takes the aggregated point cloud or the occupancy points to actually model the object and then use a variance from the Gaussian process to guide the tactile exploration. So yes, we can see from those images, you can actually use for tactile exploration, but also combine with visual exploration and then improve the accuracy result. So our question was like, is there a kind of a shape or some representation of an object or the environment that can combine this vision exploration and the tactile exploration or more modalities if possible? So there are a lot of shape representations such as volumetric representation like occupancy or density, and there's a surface representation like point cloud or mesh. But in our case, we kind of opt for the surface representation because the most of the observation you get from the vision and the tactile is very related to the surface. And even within a surface representation, there's explicit representation like a mesh, or there's the implicit representation like a distance function. So this distance function or implicit surface has been used a lot in robotic scenarios for mapping and contact detection, collision detection. And it has like nice properties such as differentiability, continuity, and so on. But the problem with this implicit representation is that it's hard to incorporate the sensor data into the this implicit because of its implicit nature. So what people usually do is they do a conversion between explicit and implicit representation to optimize or to fit the implicit representation. So one example is a superquadratic, which is the implicit surface representation and also actual parametric surface representation with a radial distance function. So how people usually do is they fit this superquadratic in the point cloud of that object and get the representation of the object. However, the problem with superquadratic is it's very the good side is very compact, but it's also too compact to represent the very complex surfaces. So the way to deal with complex surfaces is using a composition of the superquadratics. Another way of this conversion between explicit and implicit representation is using the neural networks, which is that, for example, in GenSPX, they train a neural network model, take a point cloud as input and output a distance function of it. And it has been successful in doing so. But they're usually limited to a single object, or they have in order to incorporate other modalities like color or so on, you need another neural network to actually do those incorporation with multimodality. So therefore, in this thesis work, we try to do a very similar thing with these things, but we try to overcome the limitation that might come up using these methods using a Gaussian process. So before I talk how we are actually using the Gaussian process method, I'm going to talk about what Gaussian process is a little bit. So Gaussian process GP is a stochastic model that is used for interpolation. So given an observation data points X and Y, we are trying to approximate the function F. And the way it does is using a kernel function, which is the similarity metric for two data points, and then do a prediction of the data points in the blue lines, and also do calculate the variance of those estimation that as a gray area. So good thing about the Gaussian process in active perception perspective is that incremental learning is possible in Gaussian process in two ways. One, it can just aggregate the data points into a large X and then do a block-wise inverse metrics to update the model. The other way to optimize this is that using inductive points. So we minimize the equivalent library divergence or information gain based on the observation. And then we can have a smaller number of inducing points that minimize this equivalent library divergence based on the observation and then do an incremental update. So the way we are doing is called Gaussian process distance field, which inherits these good properties of the Gaussian process, except that it uses a special kernel function, which is bijective function, like this, which is a matern 1/2 function. And then it uses something called reverting function applied to the output of Gaussian process to actually output the distance function. So if you look at the images down here, it's actually from a point cloud, it's showing a slice of this point cloud's distance field, gradient field, and the Hessian or curvature of Gaussian curvature and both mean curvature. But of course, there's always some downside. One downside is that accuracy of distance prediction sometimes lacks, especially inside the object. So this red line is the initial estimation of a distance function. So what we do is we use an iterative refinement using a sphere marching, which is using a kernel function property of the distance function. And then we iteratively refine this using some steps, usually 3-5 steps. And then it gives a pretty close distance function, which is actually where the ground truth is the black line. Another downside is that since we're applying a reverting function on the output of Gaussian process, its actual distance function is not a Gaussian process. So the uncertainty approximation of the Gaussian distance has to be approximated using this kind of a melody distance, or the one we propose, which is the Acorn function, depicted as a green and blue area in this region. So usually this uncertainty gets higher if you're closer to the object. And this is the demonstration of what result this Gaussian process outputs is that, for example, in here, we took a RGBD camera image from a simulation and converted to a point cloud, and then we fit it to GPDF to output a smooth surface of the object. And here you can see that we can control the interpolation of the this Gaussian process, and then Gaussian process gives a smooth distance field, gradient field, and also has a measure of the approximate uncertainty of the surface area. Do you have any questions? But there's always no free lunch. So the biggest problem with the Gaussian process is that it suffers from the scalability issue a lot. So we propose two methods to overcome this. One is point cloud downsampling, which reduces the rapidity inputs. And the other one is a kernel approximation of Gaussian process, which brings down the cube complexity of Gaussian's process into a linear complexity. So there are many ways to do this point cloud downsampling, but the one that I use is using a covariance matrix. So we get the covariance matrix for each voxel grid, and then this covariance matrix becomes a primitive shape. If you take the eigenvalues of non-maximum functions of eigenvectors, what am I saying? Eigenvectors of non-maximal eigenvalues. So this becomes a line in 2D and a kind of surface in 3D. And this can be incrementally calculating using a sparse data structure in GPU, and it's pretty fast. So you can see that if you have 100,000 points of this monster bubble, if we do a voxel grid downsampling, we're using 100, gives us 158 points, and we sample from those things and fit it to GPU. And kernel approximation, you can kind of think of as a linearization of the kernel. So that's like kind of basic formulation of a kernel approximation. And we have tested 3 different kernel approximation methods. First, the structured kernel interpolation C, which uses the grid points and the interpolation. Another one is using a Hilbert space method, which is the spectral composition of the kernel function. And the last one is the Nystrom method, which is the low-rank approximation of the kernel function. So you can see that they all give actual linear complexity in inference and training compared to the original Gaussian process, which has a cube and cube complexity. But since this is an approximation, there's a degrade in the accuracy, which we're going to look into. So first, within the approximation range, see the structured kernel interpolation has a kind of a discontinuous gradient field because it's using a gradient. Yes, so here the constraint for Gaussian persistence field is that it's better to use a bijective function as a kernel. As a bijective function as a kernel. So we use an inverse function of the kernel function to revert the process of Gaussian process and convert the similarity back into a distance. So that's the criteria of choosing kernel. Any bijective function can be used as a kernel, but there are, as I know, only one kernel that is bijective. That's why we are using a matron on half kernel. But if there's another kernel, then we can also use it. And if you don't need actually the sign distance, if you're okay with Euclidean distance, you can choose any other function that is not bijective but revertible. And this is the result with the voxel downsampling. So we just do a voxel downsampling on the point cloud and then fit it to GPDF and approximation method. This results in very similar thing, but with some smoothing effect. The most important thing is outside of approximation. if you look at outside of approximation range, only the Nystrom method approximation works. So in our case, if you have very few points, then using a normal Gaussian process with Boxel downsampling works. But if you have about 10,000 or more point cloud, then we choose Nystrom method to approximate this process. So we have been discussing about what shape representation of object environment we're going to use. Now I'm going to talk more about how we're going to use that Gaussian process distance field to do an exploration. So first, I'm going to talk about kind of visual exploration using a camera first. Here we follow the previous methods of differentiable rendering and to optimize the inducing points of the Gaussian process. So this is in addition to the Kullback-Leiber method we showed. So this is like you can combine them or you can use separately based on the need. And there are actually two ways to render the sign distance function. One is sphere marching, which is using a global Lipschitz constraint to progress the ray as fast as possible, and then get the intersection between the ray and the environment and use that point to render the image. The other way to render the sign distance function is using kind of a stem marching or volumetric rendering, which is taking a point on the ray with certain distance and then aggregating their information using a weighted sum to render the scene. In our case, we opt for stem marching volumetric rendering because this sphere marching has a very bad gradient calculation, which kind of takes more time for optimization of the scene. So we choose the stem marching. And another important thing about this differential rendering and active perception is that this representation is capability to deal with multiple modalities. So for example, if you're doing a differential rendering, shape is important, but the color is also very informative to optimize the scene. So what you can see is that since the distance this is relation of the Gaussian process, if we change the observation point to the modality or the characteristic we want to observe, then we can easily incorporate multiple modalities without computing the kernel metrics and the inverse metrics in the scene. So for example, if for the color image, we take the RGB values of the observation points and we do interpolation and output as the color or texture of it. And we can also incorporate very high dimensional features such as the language image clip, and we're going to show that. So this is the result of optimization, just using a color images as a demonstration. So this is a two example. So compared to neural networks, this Gaussian GPDF, Gaussian process distance field, lacks kind of high frequency details such that it doesn't have a very sharp edges like this method news, which is estimating distance function also, or the NERF, which is estimating occupancy field. However, as an outcome of the optimization, since we are optimizing the inducing points, we get an inducing point as explicit shape representation, like here. So after optimization, we can actually get the point cloud of an object, and then the more points we use, we get a better details of the object. And this is just demonstrating GPDF incorporating shape, color, and high dimensional feature. So from using a simulation data, from the shape information, we can get a depth map of the scene, and using the color information, we can get the texture of the scene. And if you compare this 768 dimensional feature of language and the image, we can identify correspondence between them. For example, if we get a feature for a word drill, then we can compare with the image and identify where the drill is in the environment.
I'm lost right now as to how the Gaussian process is playing a role here. Can you explain it? Sorry, can you explain again exactly? I mean, you could just take his image and pass it through clip, right? If you're saying you're doing something different from that.
So, so I will say Gaussian process has the capability of interpolation. So the input of this Gaussian process will be just a point cloud with the features, right?
Training the GP to predict the features.
No, we are not training the GP to predict the clip, but I'm trying to show that GP has a capability to incorporate multiple modalities and is able to successfully interpolate them so that we can have a modeling of this camera views. If that makes sense.
But in this, so here, explain what is the observation, what is the input and the output in the GP in these examples, like for the Gaussian process?
So for
Missing a lot.
So for this example, the input of GP is a point cloud with the features, meaning that point with a RGB color or display event. And then what GP can do is you can interpolate it as a distance function, like this depth image, which we are doing a rendering, but it can also interpolate these other features like color or clip in a way that it can not only it has a value on the surface, but it has a field that can be rendered properly.
I'm not sure you answered this question, but that's not.
Yeah.
Say what the inputs are.
So
What's the X and Y in the GP?
X, okay, there are multiple Y's here. So X is a point cloud with the Y. So just consider as XY as one XY set as an input, observation input. And then what we want to know is
Okay, what is the X? What's the X?
X is a point in the Euclidean space. Y is the feature of that point. So we input this observation point cloud into GP. And then what GP gives us is that if we put any kind of a coordinate point in the Euclidean space, it will give us a feature of those that point.
I think my earlier question is you are training the GP to produce the clip outputs.
Yes, yeah,
You are.
yeah. Then I will say that, yeah. So yes, that's what I'm doing. Yeah. Does that answer your question over? And if we have this kind of a differentiable rendering method, then we can quantify the information gain where in here we follow the Siemens et al. Method from Dr. Pratik Chaudhary, where it formulates the information gain like this. The important part of this information gain formulation is that the modeling or environment of the object, modeling of the object or the environment needs a capability to generate the camera views that you haven't seen. And GP does have this generated capability of making the camera views that you haven't not seen before. Usually the surface representation doesn't have a occlusion information like occupancy view, but in our case, we use an ensemble of GPDFs with different interpolation capability to mimic the occlusion effect so that we can, when we are using information gain of that we can actually get the occluded areas also highlighted as in the image. So this is a implementation detail. So we have in our setup, we have a Branca Thunder robot and two sensors attached to its in the vector, which is RealSense RGBD camera and the digitactile sensor. And they are both calibrated in respect to the end effector of the robot. And for low level controller, we use the colorless program inverse kinematics to manage the self-collision while doing the exploration. And here are the formulation where the reference velocity comes from the information gain maximization. And then there are kinematics constraint and joint limit constraint and the self-collision constraint. And this is kind of an implementation showing the robot doing regional exploration. So we have an initial RGBD image, which we converted to a point cloud for a faster initialization of the GPDFs. And then we optimize GPDF with the images. And then we select the next best view. In here, we have a predefined candidates that we give it to. And then we get a new RGBD image. And we repeat this until the maximum information gain of candidate poses converges. The result of this implementation is that, first of all, when we tried with initializing a point cloud, that definitely speed up the initialization process a lot. And another thing we noticed was that definitely our information gain accelerates the GPDS convergence compared to the random selection of the view. And this is the result of from the simulation where the blue one is guided by information gain and the green one is a random selection. However, in the real robot, because of the camera noises, it actually takes 3 or 4 images for initialization to see this kind of a drastic decrease. So as this is the GPDF result rendering a depth and color. But if you can see from the real images, there are some black areas that is actually reflective or a very sharp edge that image cannot get the information properly. So the next one was like how we incorporate tactile information into this kind with the vision. So we first talk about how to process the tactile data, and then I'm going to talk about how to find a certain surface point that we should actually touch on the surface of the object. So we use this digit sensor, which measures the deformation of the elastomer using a camera. But in order to measure the XY deformation of the elastomer, we need the black markers, which off the shelf the one doesn't have. So we actually made the custom elastomer using a mold with the bumps. So if we mold the silicon elastomer in this mold with the silicon bumps, we created multiple holes in this elastomer and we fill in the black ink inside it and cover with the reflective material, and then we assemble with the casing. And then I'm going to talk about this. And then if we do an image processing following the gel side paper, then we can get the shape information and also the force information using a tactile sensor. So we largely follow that paper, but we made some changes in the parts that I highlighted with the color titles, which I'm going to discuss one by one. So for the shape, color, there's a relationship between color and the depth with this kind of a reflective function relationship. So the gradient of the color image in respect to the pixels have a relationship with the color gradient. So what we can do is if we find out this reflected inverse reflective function, we can take the image pixel colors and convert it back to the depth gradient, and if we use a Poisson solver, we can get the actual depth. However, this reflective function is very nonlinear and is not known for this elastomer. So what we do is we model as a 2x11 matrix, and then we calibrate using this kind of a formulation where this reflective function is a metric multiplication of this value, which is the color pixel in pixels colors and its neighbors pixels and its pixel position. Then we can get the approximation depth, which is a deformation in z-axis. And for XY deformation, like I said before, we have to track this black dots and then check the XY, how much it deformed from the original position. But the problem with the previous methods using a Kalman filter or the Hungarian algorithm on it is that it cannot handle the collision effect well. And so if you miss some observation of this plot, you won't be able to estimate the proper deformation of that point. So what we do is we use coherent point drift algorithm, which is originally used for non-rigid point cloud registration, that can also work in the case that there is no one-to-one matching directly. So if you look at this image, even if you don't have a one-to-one matching on the bottom side of the fish, you're able to successfully match using a covariance of this information. And the last, if you have a deformation matrix, which is meaning that if you have a deformation XYZ of those points, by doing a matrix multiplication with the stiffness matrix, you can get the force out of it. However, this stiffness matrix is not known, so what we do is we calibrate this stiffness matrix using a force measurement from the force torque sensor on the bottom of the tactile sensor, and then we try to match the sum of these forces to the force torque sensor. And this is kind of a result showing this measuring the forces using an XYZ deformation. So for tactile exploration, what GPDF gives us is the surface uncertainty that as we saw before. So what we have to do is we have to take a gradient S and going to the most uncertain surface point, but confined on the surface only. So what we can do with that is actually doing a projected gradient ascent on it to go to this area. But when we calculate the gradient of the variance of the Gaussian process estimation, we actually get a free distance and the surface normal information. So instead of doing this as a two separate stage, in order to speed up the computation of this gradient ascent, we utilize the distance and normal information that we already obtained from calculating the gradient of the variance. And this is the demonstration of this process. So the blue points are incrementally trying to go to the surface area that has a higher uncertainty. So in the 100 steps, you can see that it goes to the backside of the object that has not been seen before, which is the red points. So this is the pipeline for the tactile exploration. So we assume we first have a visual exploration that has rough estimation about the environment. And then we identify the most uncertain surface point to touch. And then we get the contact points using the Fourier kinematics and using a tactile sensor. And then we incorporate this to the Gaussian process using a block matrix calculation. And then we repeat this until the maximum information gain or maximum uncertainty kind of converges. So what we saw from doing this was that this tactile surface uncertainty was able to identify the areas that was noisy in the camera, which was a reflective area of this red hole or sharp edge of the wooden box. And then it tried to touch those areas first before the other areas. Then we could also see, this is it might be a little obvious, but the maximum uncertainty of the scene that we were trying to explore was keep decreasing as more contact points are integrated into this exploration. So now we have a camera and a touch sensor to explore the environment. So, but we wanted to see if we can incorporate other modalities or do an exploration of other object properties. Since we know the Gaussian process can take any other modality in an easy manner. For example, if you have a temperature sensor that can measure the temperature of the surface, we can incorporate the observation to the Gaussian process distance field, and then we can estimate the temperature of the Fourier points that you want to know about. However, we first wanted to ask if we can get more data from the tactile sensor, and then try to estimate some materials of the object and like object properties of the object. So we tried to kind of explore this area and try to see what we can do with it. So we collected data of different materials, like these 8 materials, and already for the table and hull, which has a very visible texture feature, you can see the difference between of the image of this tactile sensor. So we know that sliding like strategy, like sliding through on the surface, gives a very good is a very good strategy to the exploration of object property. But the problem was that the sensor was keep wearing out when we were doing the sliding strategy. I almost cried when it broke. So I had to recode it again. So we changed our strategy back to kind of a rolling strategy, going like touching the surface and like rolling left and right, which might be not as effective as a sliding strategy, but we tried this so that we don't wear the sensor. Yeah, that was a video. So yeah, this is the depiction of the rolling strategy. So what we did was for each material for 3 trials, we did a 70 rollings for each. And then we got the force amplitude in XYZ, which is a low frequency feature. And we tried to kind of see if we can identify the materials by training the classifiers on this 3-dimensional feature. So the random guess rate, these materials will be 14%. And then we tried the support vector machine with their perceptron and their random forestry on it. And the result was it was better than a random guess, but it was not that high in the cross-validation. But we believe that if we can, rather than just using a feature with 3 dimensions, if we can use the full image feature or the higher dimensional feature, we believe that we can get some distinguishable, we can distinguish the materials better. Yeah, but that was. So in summary, I talked about how we can incorporate multimodalities using this Gaussian versus distance field. And we showed what exploration strategies can be done using this kind of a representation of an object and environment. And we think there's a potential for incorporating more modalities like other object properties in this GPDF to do a more informed exploration and improve the robust capability. So the current limitation we see is the kernel's expressiveness. The kernel only takes the point cloud with the feature. But we want to see if we can actually deal with more complex primitives as the input to the Gaussian versus distance field. And we already kind of have a primitive result on some part. So instead of just taking point position as the input, we are actually also considering the radius of the point with it so that we can express more complex shape, even though they're all in the same position. Another part is the differentiable rendering is not that efficient. So the exploring like how computer vision people are doing recently, doing some kind of a approximation or doing kind of using a special architecture to speed up the process might be a good area. And we showed some exploration strategies, but there are a lot of exploration strategies to explore. And then it would be nice if we can create more human-like behavior where we consider the trajectory instead of just a point, or doing this in a real-time manner without just taking some seconds to optimize and to explore. And there are others also. These are the references in this work. Yeah, and I thank every LAM members who came today, everyone here. And I mean, I got a lot of ideas by discussing about this thing with LAM members and Nadia Figueroa and Dr. Rizana, and even like the 1-hour meeting I had with Dr. Michael. So I had got a lot of ideas just from it, and I thank everyone for giving me this idea and supporting me. So.
Right. Any questions?
Yeah, I have many questions.
Yes.
As you can imagine, I couldn't see well, but did you say class D and Letterman?
Plus in Letterman for the
Yeah, they were the pioneers 40 years ago, and they have in that title of their paper is exploratory procedures for tactile features. So they show that people use different hand movements in order to get different features of the pressure.
Yes,
Yes.
yes, so it's the paper that we cited. So
Yes,
that's
yes.
why we wanted to do sliding
Yes,
first.
yeah.
Yeah.
Yes, yes, yeah,
Just want to
You're
make
talking
sure,
about-
yes,
yes,
absolutely.
Class, yeah,
that's
class,
good.
yeah. So this is a different
Yeah,
exploration
they
strategy.
call it actually tactile exploratory procedures. Yes, yes. Now, the other thing, I think I sent you, my very last PhD student at Berkeley was Caroline Chen. I'm fine, but she studied moving,
Which one?
moving
Or,
field, yeah. And she was able to detect liquid versus something like a sugar. I don't know.
granular object between the victims.
Yeah, so I think I sent you the paper. If I didn't remind
Yes, I will check again.
yeah, check it, because that fits very much into the agenda. As we go from physical materials. Then, kind of like this.
Yes, yes, so the assumptions in the thesis were that, like, we assume first rigid objects, but obviously the next frontier would be like non-rigid in the form of more
Especially
granular.
since it- because I'm interested in kitchen.
Yes, yes.
And then we have all sauces and all kinds of materials that you have to use, so that thing. She is coming from that, so. That's
Yeah, so definitely, currently, I think I mostly deal with kind of a static environment with kind of steady objects, but definitely going more onto the dynamic material or like very complex non-rigid material will be
Yeah.
Interesting area.
I'm sure I said that, but maybe I could say to them all. Thesis, something.
I will look at it.
It's also relevant to like mechanical engineering, but it's relevant to all the construction. Cement. Sand.
I think there are like almost infinite possibility of this exploration strategies. I think that will be interesting area to look into, you know, what kind of strategies we can use for robots to actually learn
She
about
was
this.
very creative during the COVID. She took care of about at home. She set up a lab at home. Cleaned the kitchen.
When you were showing the results of incorporating the tactile information into your GPF, were you holding the information that you had previously gotten from the camera fixed and then incorporating the info from the tactile sensor? Or were there like incoming streams from both?
In here, I was fixing it and then aggregating using, you know, I talked about two ways to update the Gaussian process in incremental manner. One is aggregating the data points and the other is kind of doing an optimization of the observation point. But for tactile, I was fixing a region and then just aggregating it, aggregating the information. But it is also possible if you want, you can just do this for the library divergence optimization using and also the differential rendering altogether. But I mean, it depends. But for this case, I found that aggregating is easier.
Yeah, have you thought about, so like you use the perception data to figure out what needs to be explored and used, and then use the tactile sensor on the shiny points to figure out the edges of it. Have you thought about using semantic information from the image to understand more about the material. For example, your rolling strategy or sliding strategy could be informed using knowing if the surface is rubbery or smooth.
Haven't done it, but I mean, that's definitely one way to do it. So if Clip gives a full pixel information about the image, you can use same differential rendering method to optimize this reducing point of the Gaussian process, and then do a exploration, just like color, but do exploration for the semantic information, which will include this kind of material information, but I haven't explicitly tested out.
We talked about this a little bit when we spoke, but I'm still not sure why the GP is the strategy here. Compare it against anything like a nerve or like Gaussian sliding or
Gaussians, maybe, I think all these methods are, what all these methods are trying to do is, interpolation of the data points that it has, like based on, and doing some optimization based on the observations. And Gaussian sliding, I guess, is a good way to represent the surface of the object also. But the reason why I chose the GP is that, first of all, it gives the distance function, I think, which is useful for, which I believe is useful for robotic control scenarios. And then the other reason was that it gives it is easier to incorporate the tactile information. So there are actual papers that uses the Gaussian splitting and also GPIS to combine the vision. It's not actually exploration in vision, but just get the vision information and the tactile information merged kind of together. But I felt that that is not actually I thought that was not a complete way to kind of combine the vision exploration and tactile exploration together. I felt that there has to be some unified representation that can measure the information gained in both tactile and the camera at the same time, not just separate. But yeah.
so that's the one that you can also have something like a STF. I'm still kind of hung up on YGPs, right? It's a computationally rough approach here. It's unclear to me, and maybe you have good evidence of this, but it's unclear right now of how much you're getting from the uncertainty estimates that come out of the GP, like how well grounded they are. We talked a little bit kind of quickly about these tricks you have to make something approximately calculable. So I mean, the naive thing I would throw out this would be something like an ERG or something like a STF. Here's why it goes.
I believe I think for vision only, like NERF kind of a method offers a good way to measure actual more than NERF, Gaussian splitting. It also gives explicit representation of the environment and has a very efficient calculation of the hashing to calculate the information gained. The vision side, I feel like Gaussian splitting is a good way to do it. But incorporating tactile data seems to be a little not intuitive, because where you have to combine your uncertainty location to the surface while finding a maximum information gain. And I felt like this distance function where the GP actually gives us has a better capability of doing those both at the same time without going back and forth. The DFS, for example, it is DFS is trained on multiple point clouds to convert the mesh. But in that case, then incorporating the color in addition to the shape becomes a harder problem. You basically need another neural network like the nerve. So I think that was a kind of a thing I tried to avoid, having a multiple neural networks that is trained for separate information such as like a shape, color, or anything else. But I felt like GP was easier tool to just incorporate that by just changing the observation of this point. So yeah, I think better comparison, I don't believe it's the best. Yeah, I think Gaussian splitting is a better comparison, which is also not neural network. But But I felt like doing a constraint optimization on the Gaussian splitting has also some constraint because it doesn't have the distance information or the interpolation of those Gaussians. So yeah, that's what I think. Yeah. But it will be what I actually want to explore is that. So I believe this Gaussian process is I mean, there has been a lot of work in kriging, like kriging and spatial mapping, and they use this Gaussian splitting to interplay the data points. So I believe that if we can interplay more complex shapes instead of a point cloud, then I believe that this GP still have some hands-on those parts. So I think the kernel is, of course, the important part, and maybe kernel can be trained with neural networks or something else, but I think it's really. I'm not sure that was satisfying to us. Well, there was a question from. I might have missed this. Can you talk more about how you're doing exploration planning? Are you thinking about?
Please repeat out loud.
Okay. Can you talk more about how you're doing exploration planning? Are you thinking about camera views collected over an entire trajectory or only at points? Also, presumably, you can trade off quantity versus quality of data by getting closer or farther from the object. So first question, am I taking the trajectory or a point? Currently, I'm taking a point, but trajectory also seems feasible because the seeming has original work. They actually do a trajectory of, they optimize for trajectory of a drone for like 40 time steps and using some sampling based methods. So if you can do that, I think we're also able to do that, but in this work, we haven't done it. And the second part, also presumably you can trade off quantity. Yeah, so this is very good point. So for example, if you have a RGBD camera, if you go actually just closer to the surface, you can get actual better estimation of the depth. So actually there's like kind of quadratic relationship with the noise of this depth observation and the distance of actual from the camera to the object. I haven't showed the slide here, but Gaussian process formulation I showed you assume kind of a uniform variance of the observation points, but you can actually incorporate the input noise in this formulation and then have a different variance on each data points. So I haven't done it, but I believe it can try that kind of exploration strategy where you can go closer and farther using the GPDF. Yeah, but this work I haven't explicitly mentioned about it in this.
I have a question. So having this experience of building the sensor, like what would be a more ideal sensor to actually get these properties that we want from the objects? Like, do you have any intuition on what materials would be necessary, or like, should we get another type of sensor that's not camera based or something like that?
Try to speak into this from directions. One, if you just decide to stick with the camera, there are so many pipelines you have to calibrate in this sensor. So if you're doing some tests that camera sensor doesn't have to be curved and it can be just flat, then I feel like we can just have a flat silicon that is just as a plate, and then just do a CNC cutting, and then have some markers on like not the non-markers, but have a kind of a pure code like a marker that can also check the orientation of the contact points, not just the position of the contact points. So maybe if we stick to camera, I think that's the most practical way and robust way, because in that way we can easily replace the silicon or the usually the flat silicon or more durable than the molded silicons. That's one way I see. And the other way, if we don't use the camera, there's a capacitance-based sensors and also the pressure-based sensor. I believe the capacity-based sensors can be have more high resolution. I mean, they're already using a MEMS technology, but to me, it seems still too big. So maybe using multiple of those MEMS sensor or MEMS chip might have a better with the higher.
I expressed. Yes. There is. That's part of this. So,
Actually, I think that's one.
We do use it.
Huh?
We do use force sensor.
yeah, but
Not all.
Okay. Here he used it to calibrate the tactile sensor, so you can understand, because the force torque sensor would be mounted on the end effector. So we might not get like the best measurement of force. So like what he did was calibrate the tactile sensor, but we do use a force sensor. Yeah.
I apologize.
Yeah.
I missed it.
Yes, I'll just, yes,
There's a force sensor to calibrate the tactile sensors, and tactile sensor is the approximation.
The closed session, yes, yeah.
So thank you, everybody, for coming. We'll give a round of applause.